Do we have this balanced? What you got, Allison?
You want just the coefficient?
Yep, give me the coefficient.
I got 3, and then 2, and then 1, and then 6.
Oh, that's what I got.
I didn't finish.
But it's not that.
Is that right?
That's right.
It is? Yeah.
At first we had 2 hydroxides on the left and only 1 on the right. So you'd think, okay, I'll put a 2 there in front of the sodium hydroxide to balance the OHs. 2 there and now 2 there. But with the other things, I'll have 2 sodiums then and 3 sodiums on this side. Well, if you have 2 of something on one side and 3 on the other, get 6 on both sides. That's where we'll put a 2 in front of that to make 6. Change that 2 to a 6, and now that means I have 6 hydroxides. I've got to come back here and put a 3 in front of this. That takes care of the calciums too. So again, keep the polyatomic ions together. And just think of them as a single unit rather than individually P's and O's and O's and H's. The O's, balancing the O's will make you crazy. Yeah.
Would I get it wrong if I accidentally had a double? Because like that's what I had.
Oh, if you would have had 6, 4, 2, 12, I would mark it wrong. No, that's fine.
Alright. That's fine.
If you can reduce it, if you realize that you can reduce it, then
Yeah, I
do
just
this.
didn't realize.
Yeah. I wouldn't mark it wrong. You've got it balanced.
Yeah.
And so that's good with me. Yep. All right. Now, yesterday we talked about exothermic and endothermic. And we saw, I ran around the classroom and showed you what it feels like, to have an exothermic reaction inside of a beaker and then an endothermic reaction. Now, I've got a couple other examples for you. When cookies are baked in the oven, is the baking of cookies an endothermic process or is it an exothermic process?
I have no idea.
It's endo.
The question is, that's right, you're right. Is heat going in to the cookies or is heat going out of the cookies? It's going into them. It's an endothermic process. I want you to think of it like this. This is our system. In this case, that's the baking cookies. If the heat's going in, this is endothermic. If the heat's going out, that's an exothermic process. So in the case of baking cookies is endothermic. You have to put heat into the cookies. Yeah. And what about gasoline burning? Is heat going in or is heat going out?
Out.
Yeah, anytime you burn something, heat escapes. Heat's given off. Heat exits. So it's exothermic. If you want to. If you understand the difference, then no. All right, what about this? Here's a good one. Freezing water.
That's moving on.
You want water to freeze, so do you have to put heat into the water? I mean, in the box here is the water. Is heat going into the water to get it to freeze, or is it going out of the water to get it to freeze? Yeah, you were right. I was just pausing to make sure that you felt confident.
Okay.
Freezing water is exothermic. Now, when you try to relate, yesterday I put an exothermic reaction on your hand or your arm, and it felt hot, right? That doesn't mean everything exothermic is hot. You okay with that?
Yeah.
It's not. In the case of freezing water, it's not hot at all, it's cold. But the process, the energy is going out of the water to get it to freeze. So that process is exothermic. Now, of course, baking cookies, you have to get the cookies hot to get them to bake. But that's still an endothermic process. So the temperature by itself doesn't really indicate whether something is exothermic or endothermic. It's the flow of heat. Is heat flowing into the system, or is it flowing out of the system? Like the case of burning gasoline. The gasoline burns, heat flows out of that system. So if you want to boil water, you have to put heat in, or does it give off heat? You got to put heat in, so that would be an endothermic process. Yeah. Everybody catch that?
Yep.
Boiling water is endothermic. All right, good. Now, one other thing that actually two other things I want to mention about chemical reaction. This is new, so if you want to write this down, it's probably a good idea. There's these things, and I know that you learn about this in biology class, catalysts. I think you learn about that.
Yeah.
You know what a catalyst is? What's a catalyst do for a reaction? Yeah, it's something that you can put into a reaction to get it to speed up. What else do you know about the catalyst? Not only does it speed up the reaction, but what else about it? What happens to the catalyst itself? No, it's actually the opposite. No? Actually, no, that would be the opposite. The fate of the catalyst is that however much catalyst you put in to get a reaction to speed up, that same amount of catalyst is there at the end. It doesn't get used up. A catalyst speeds up a reaction, but it itself does not get used up. I'm going to show you on Monday a reaction that has a catalyst. It's the decomposition of this substance. This is something that you know. I don't know if you know it by chemical formula. Do you know what that is? Almost looks like water, but it's H2O2. What is it? Do you? Huh? Oh, it rhymes with that. This is hydrogen peroxide. Hydrogen peroxide. Is that what you said?
No, it's hydroxide.
Yeah, that's what I thought you said. No, this is hydrogen peroxide. You know hydrogen peroxide? Do you know what that is? You can get it at the drugstore. It comes in a brown bottle. If you get a cut, it's a good disinfectant. Now, hydrogen peroxide is quite reactive, and by itself, it will decompose. It's a slow process. It decomposes into these two things. It decomposes into water and then oxygen. And if we wanted to balance this equation, we put a 2 in front of that, 2 in front of that. Now it's balanced. To get this reaction to speed up, which again, it's a very slow process. This takes a long time. You can wait years, and the hydrogen peroxide is very slowly decomposing. So if you have an old bottle of hydrogen peroxide, it may not have any of this in it anymore. It might be all this. Because it decays, it decomposes. You can get this reaction to speed up, and you're going to see this next week, by the addition of a catalyst. And usually when we add a catalyst, because a catalyst is not really a reactant, because it doesn't change, it's just there, we'll write this presence of a catalyst above the arrow. Like the catalyst for the hydrogen peroxide is commonly MnO2, manganese dioxide. And we would write the presence of a catalyst above the yield sign, like that. So if you ever see a substance that's written above the arrow, it just means it's there as a catalyst. And since it doesn't get used, it should not go in the reactant side, because reactant implies that, oh yeah, this is going to break apart and rearrange. Well, this stuff does not rearrange. It's just there. So, I should probably just give you a good working definition. A catalyst, a substance that speeds up a reaction, but doesn't get used. Now, I've used this one as an example. MnO2 is not the only good catalyst out there. There's a lot of good catalysts. But I just want to mention that anytime you see a substance that's written above the yield sign in a reaction, that's what it's doing there. It's saying, okay, this is a catalyst. The reaction occurs in the presence of this stuff to get it to go faster, or to go at all. One other thing that I wanted to show you before we start getting into types of reactions is very often when a chemical equation is written, not only are the formulas of the substances and the reactants and products given, but also physical states are given as a subscript right next to each term. So what this means is when you have sodium plus water, it will yield sodium hydroxide and hydrogen. The physical states give us a more clear picture of what we would actually see if we were to observe this reaction. a solid chunk of sodium, so the S stands, of course, for solid, is added to a sample of liquid water, that we have an L next to water for a liquid. And that's going to produce hydrogen gas, so you see the G there for gas. And then the other product, I gave this out of order, it doesn't matter what order you give them, but then we have this AQ. AQ. I've heard of solids, liquids, and gases. What is AQ? Well, AQ is a different one. As a physical state, AQ indicates the word aqueous. Aqueous is a Latin word. Anybody want to take a stab at what aqueous might mean? Yes, who said that? Anthony, where'd you get water from? Yes, Spanish, aqua, right? It looks kind of like that. Yeah. The word aqueous means dissolved in water. And very commonly in chemistry, reactions will occur while they're dissolved in water. So aqueous is a very common physical state that we're going to use. You'll see aqueous show up all the time. So it's a good idea to write this down. AQ means dissolved in water. So the sodium hydroxide, the NaOH that's formed in this reaction, is a soluble substance. So the fact that there was water there, the sodium hydroxide just stays dissolved in the water. A lot of times when things are aqueous, you can't even tell they're there by looking at it. It just looks like water. But you do have something dissolved in it, so that's indicated by that. So these are the only common physical states you're going to see. I'm just trying to think very quickly. I do a lot of chemical reactions, and I don't think there's any other physical states you'll ever see. Ever. Solid, liquid, gas, and then aqueous. Now we know there's plasma, but I don't know anything about the reactions of plasmas, and I think when it reacts, a plasma it would just be a gas. Okay, anybody have any questions about that? So we'll see a lot of AQs in this chapter. What we're going to do now, and this really is what we're going to finish the chapter with because we don't have much time for anything else. Types of chemical reactions gets pretty big. And this is the part that I need to scale down a lot. I was hoping to give lots of details about different kinds of reactions. We don't have the time anymore, so we're just going to give or see a bit of an overview of the types of reactions. There are 5 types of reactions that you need to know about. There are other kinds in chemistry, but in the context of a Chemistry 1 class, 5 basic kinds of reactions you should know. You should be able to recognize these. I would have you completing these reactions, like I would just give you reactants, you'd have to write the products, if we had those extra 3 days. But we lost them. All right, so the first one is one that you've done before in this class. It's the double replacement reaction. The pattern for a double replacement reaction looks like this. I've got A's, B's, C's, and D's, just as generic symbols for ions. As you're writing that, think of what were we doing in this class when you learned about double replacement. We've done this before, earlier in the year. Does anybody remember doing anything with double replacement reaction? There was a lab that we did. Do you? What was it? Can you remember the lab? That's right, that was it. The chapter that we did on naming ionic compounds, we did that 6 solution lab. You had 6 test tubes on a rack, and you had to determine what was in the 6.
Oh, that was not my favorite.
I remember that one. Yes, we remember that one.
Yeah.
That was the kind of reaction that was happening. What we have is an ionic compound. Remember, ionic compound is positive, negative, and this one is positive, negative. And it's like the double date analogy where the 2 couples will switch partners. The A will go with D. Remember that ionic compounds are always given with the positive ion first.